Hey guys, today we're going to be talking about rational exponents and negative exponents. But before we get into that, I just want to do a really quick recap or just a quick concept check for those of you that don't fully remember or maybe even don't know how to do an exponent to a fraction. So real quick, let's break down what an exponent is. Just a quick reminder, an exponent is multiplying something by itself that many times. So for example, if I have 2 to the 2, I multiply 2 by itself too many times. That many times. If this was a 3, like that, I'd multiply 2 by itself 3 times. That's all an exponent is. So when we look at exponents and fractions, it's basically just that. We're saying, okay, 3 over 4 times 3 over 4, just like that. And what that is 3 times 3, it's 9 over 16. Sorry, that's a little small. 3 times 3 becomes 9, and 4 times 4 becomes 16, just like that. But we don't always want to write this out. If we have a really big exponent, we don't always want to write it out. An easier way to do it is simply run the exponent through the numerator and into the denominator. So it becomes 3 squared over 4 squared. And we still get the same answer because it's the same thing. 3 squared is 9 and 4 squared is 16. Just like that. So now that we hopefully have our recap on, fractions and exponents, let's jump into negative exponents. So if you came to this video for just the rational exponents part or just the negative exponents, I'm going to leave little timestamps in the description below, so go check those out if you want to skip ahead to rational exponents, or stick around if you don't know negative exponents. But let's talk about it for a second, and let's make a table. This is a table of, not negative 2, just 2 to the x. So when x is 2, so 2 squared, what is 2 squared? Well, it's 4. Okay, when x is 1, 2 to the power of 1, well, that's just 2. And when x is 0, well, anything we know to the power of 0 is just 1. And let's stop right there for a second. Hopefully you guys are seeing the pattern. This is dividing by 2 every single time. It's dividing by our base, right? And if we were to keep this going, let's say out of 3, well, 2 to the power of 3 gives us what? Well, 8. And to get from 8 to 4, we divide by 2. So there's a clear pattern going on, and this is actually how we determine what exponential growth is. This is what it is. It's as x increases, y increases exponentially by a factor of the base. This is exponential growth by every definition of the term. We multiply by 2 every single time. And when we want negative exponents, we're essentially doing the same thing. Now, you might be asking, well, how do I multiply 2 by itself negative 2 times? Well, you can't do it. Well, theoretically, you can't multiply something by itself a negative amount of times. A lot of you might be thinking, okay, well, if I divide 2 by itself by 2 times, well, 2 divided by 2 gives us 1. And is 2 to the power of negative 2 equal to 1? No, it's not. It's equal to 1 over 4. How do I know that? Because if we're dividing by 2 every single time, and this scale is, not changing at all, we're just going up by 1 or down by 1, then we must divide by 2 to keep it going. So what is 1 divided by 2? Well, it's 1 over 2. Okay, and what's 1 over 2 divided by 2? It's 1 over 4. Dividing it all by 2, just like that. And essentially, that's all negative exponents are. And I'll simplify it for you in just one moment, but I'm hoping that we're seeing something here. When it's positive 1, it's 2. And when it's negative 1, there's a 2 in the denominator. When it's positive 2, it's 4. And when it's negative 2, there's a 4 in the denominator. The pattern here is, and basically how we do negative exponents, is simply by doing the following. If we have 2 to the negative x, it just becomes 1 over 2 to the positive x, just like that. And then from the previous rule, the x just gets put through, so it's 1 to the power of x over 2 to the power of x. And well, we know 1 to the power of anything is just 1, so it's 1 over 2 to the x, or whatever our base is. If we had a base of 5, it would be 1 over 5 to the power of x. And that's really it for negative exponents. That's all a negative exponent is. Whenever you see one, the only thing you have to do is just put 1 over the whole thing and change the exponent from a negative to a positive now. Just like that. And a little shortcut, because it gets a little harder, but a little shortcut when you have fractions with negative exponents. So let's say 3 over 4 to the negative 2. Just like that. Well, this becomes 1 over 3 over 4. This whole thing becomes to the positive 2, right? And, well, what is 1 divided by 3 over 4? Let's just rewrite it. 1 divided by 3 over 4. All this is just squared. When we divide a fraction, I hope you guys remember, but we just flip it and turn that into a multiplication. So this becomes 1 times 4 over 3 squared. And, well, 1 times 4 over 3 is just 4 over 3. And we're left with 4 over 3 squared. And I'm hoping you guys see that 4 over 3 squared is just a flip of that, 3 over 4, with a positive exponent. Anyway, that's like the little shortcut with like the math behind it. What I was trying to get to is when you see something simple like this, you can very easily just look at it and be like, okay, that's the same as this, 4 over 3 squared. All I did was flip it, and I changed the exponent to a positive. Now let's talk about rational exponents. Okay, so now moving on to actual rational exponents, let's talk about them for a second. So a rational exponent is an exponent that's a fraction, basically. If I have 2 to the power of 1 over 2, this is considered a rational expression, a rational exponent. So what is happening with rational exponents? How can we multiply something by itself half an amount of times? And when it's worded like that, some of you might get it, some of you might not. That's okay. Let's talk about its table. X and Y once again. And this time I'm going to do 4 to the power of x. So let's do 1 over 2, multiply that by 2, 1. Let's multiply 1 by 2, 2 by 2, and you know what? That should be fine. So real quick, let's do this. So what is 4 to the power of 4? Well, it's 256. Okay. What's 4 to the power of 2? 16. Well, what's 4 to the power of 1? Well, it's 4. So once again, we're going to look at the pattern here to evaluate 4 to the power of 1 over 2. And let's take a look. So here, we're dividing by 2 every single time on our x-axis this time, not our y. Right? So it's constant, but it's not constantly like going up by 1, by 2. This time it's being divided instead of added. Okay, so now that we know what's happening to our x side, let's look at the y. Well, what's happening to y here? So to get from 256 to 16, what are we doing? We're dividing it by 16, or in other words, we're also taking the square root of 256. 16 squared gives us 256. Okay. Well, how about from 16 to 4? What are we doing there? I'm hoping you guys see that we're taking the square root of 16 to get from 16 to 4. Well, how about from 4 to a half? If that's constantly, we're taking the square root constantly, that means we must follow this. So to get from 4 to a half, we're just going to take the square root of 4. And that's 2. Okay. Go ahead and plug 4 to the power of 0.5 or 1 over 2 or anything like that into your calculator, see what it gives you. And it'll give you 2. Okay. This tells us something right here. And this is like one way of learning it. The other way is just looking at the, I guess, equation for it. This is the understanding behind it though. And my theory about math is that if you understand what's happening, why it's happening, then you'll understand math and you'll bang every test. You'll find it fun. If I'm being honest, it really is. But back to this. This is what's happening. We're taking the square root every single time. And if we were to change the axis, let's change this axis now into thirds, for example. Let's do 27 to the power of x, for example. Okay, so another example, a better one I should say, is 27 to the power of x. If we take a look at 27 to the power of 9, for example, we get a massive number, 7.6 times 10 to the 12, so on. Sig figs if you're a physics student. If you're not, you have a whole lot of decimal points right there. But 27 to the 9, and let's take the third root of that answer. And we get 19,683. So the third root of this, I'm just going to write 27 to the 9. The third root of this gave us this value right here. Okay. Well, let's try again. What's the third root of that value? And hopefully you'll notice the third root of that becomes 27. And now we've established a pattern here. We're taking the third root of our previous value. This one here would be the third root of 19,683. So what's the third root of 27? Well, it's 3. Right? We want to get the third root of 27. Now, a lot of you might be asking, how come this time we're doing third root, last time we did square root? Because last time, here, it was going up by increments of 2. Now, we're going up by increments of 3. And not addition. We're actually doing multiplication and division this time. As we go up, it gets smaller by 3 every time. So now that we've established kind of what's going on, we can see that this value, when it's a 1 on top at least, this value becomes our root value. So whenever we have a value to the power of 1 over something, that becomes the root. Now, what if we have something like this? That's where it gets a little bit different, but it still stays the same. And I'm not going to use a table this time. I'm just going to flat out give you the equation. But here's what happens. The denominator, the n, or in this case the 3 or whatever, becomes, oh my bad. The denominator becomes our root. It becomes like the root, what we're taking the root. The x stays in here, and the numerator actually becomes the exponent of the term. Now this can either be written like this with the m on the inside of the whole thing, like that, or it can be written like this. We could take the nth root of, my bad. We can take the nth root of x and then put the whole thing up to m, just like that. And I'll show you a really good example of like both the ways we could do that. So 27 to the 2 over 3 actually works really well. We can either take the third root of 27 squared, or we can take the third root of 27 and then square that, just like that. And these are the exact same thing because in the end it gives us the same answer. Here, if we have the third root of 27 squared, we get the third root of, I don't have my calculator, sorry. 27 squared gives us 729. And the third root of 729 is just 9. Okay, this one. What is the third root of 27? Well, it's 3. And now we just have 3 squared. And it's 9. So that's just to prove that these are the same thing. It just really depends on how you would like to do it. And more often than not, there's one clear, easy way than another. In this case, I'm hoping you guys see that it's this one, because 27 squared we can't really do off the top of our head. However, this thing right here, we could do it all in our heads just like that. But yeah, that's basically rational exponents. Anyways, guys, that's it for rational exponents, negative exponents, and just a review of like fraction exponents. If this video helped you, please share it, I guess. Leave a comment if you want me to do anything else, math or physics related, any concepts, any specific questions, anything like that. Make sure to check the description. I'm going to leave a link to another video of me basically solving a bunch of these, giving you a feel of how to solve them or how to simplify them, stuff like that. But yeah, make sure to go check that out. If you haven't already, go check out the exponent laws video, posted about a week ago. But yeah, hope you guys have a great day. Peace.